July 3, 1938, East Coast Main Line, England. The engineering calculations from German and American railway specialists visiting Britain's most ambitious locomotive trials would never capture what they witnessed that Sunday morning: a streamlined steam engine achieving velocities that defied everything traditional railway wisdom said was possible about mechanical propulsion. Through the coal smoke and steam of the test run preparation, the LNER Class A4 locomotive stood gleaming in its garter blue paint, its body shaped like nothing European or American railways had attempted before. No exposed machinery, no traditional locomotive profile, no acceptance of the speed barriers that had killed test crews and destroyed engines across Britain's railway system. Yet this streamlined machine was being prepared for speeds that conventional locomotive design could not safely achieve. In British railway engineering, master builders accepted that steam engines became dangerously unstable above 100 miles per hour. The mechanical oscillations grew exponentially with speed, creating forces that shattered connectors, cracked boiler plates, and derailed trains with consequences no one could predict. The engineers were operating with a locomotive philosophy the railway establishment had never imagined possible. Aerodynamic streamlining to reduce wind resistance, double-chimney exhaust systems for maximum efficiency, precision balancing that distributed forces evenly at unprecedented speeds, mechanical stability that would endure not just higher velocities but sustained operation beyond what conventional steam technology achieved. 3,000 miles from American locomotive workshops, the most decisive speed revolution in railway history was revealing itself. Not in larger boilers, not in traditional steam engine design, but in the systematic precision that integrated every component of the Mallard in ways conventional railway engineering never imagined possible. The speed barrier had claimed lives before. In 1935, a German locomotive attempting high-speed trials had suffered catastrophic mechanical failure at 118 miles per hour, its connecting rods shattering under forces the designers had underestimated. The wreckage scattered across 200 yards of track, and the incident convinced many railway engineers that steam technology had reached its absolute limits. American railways had abandoned high-speed steam development entirely, shifting resources toward diesel-electric locomotives that promised reliability without the mechanical violence that destroyed steam engines at extreme velocities. The Milwaukee Road's Hiawatha locomotives held American speed records, but even those carefully designed machines rarely exceeded 110 miles per hour in regular service. British engineers faced additional constraints that made high-speed operation even more challenging. The East Coast Main Line's curves and gradients demanded engines that could accelerate rapidly, maintain speed through difficult terrain, and stop safely using braking systems designed for much slower operation. Traditional locomotive design prioritized power over speed, accepting that mechanical limitations would prevent sustained high-velocity running. Sir Nigel Gresley, the London and Northeastern Railway's chief mechanical engineer, had watched these failures with the analytical precision that defined his career. He understood that breaking the speed barrier required not just incremental improvements to existing designs, but fundamental reconceptualization of how steam locomotives converted thermal energy into mechanical motion. The Mallard would prove that steam technology still possessed capabilities the railway establishment had declared impossible. The morning of March 7, 1933 promised nothing different from the dozens of high-speed test runs that had preceded it on Britain's railway network. The LNER Pacific-class locomotive had been prepared for velocity trials north of Grantham. Its crew experienced the dangers of pushing steam engines beyond conventional operating limits. Driver James Harrison had logged over 20 years on express passenger services, earning a reputation for smooth handling and mechanical sympathy that extended locomotive service life. He understood the sounds that indicated approaching mechanical failure, the subtle vibrations that warned of connecting rod stress, the changes in steam pressure that signaled boiler problems developing before gauges registered danger. At 95 miles per hour, the locomotive's behavior remained normal. The rhythmic beating of wheels against rail joints, the steady exhaust from the chimney, the controlled oscillation that all steam engines exhibited at speed. Harrison had operated locomotives at these velocities dozens of times, always remaining alert for the signs that indicated approaching the machine's safe limits. The failure happened at 23 miles per hour, when harmonic oscillations in the locomotive's motion suddenly synchronized with the natural frequency of its mechanical components. The connecting rods that transform piston motion into wheel rotation began experiencing forces that exceeded their design specifications. Metal that had withstood years of normal service started flexing in ways the original engineers never anticipated. Harrison felt the change before he saw it, a roughness in the locomotive's motion, a vibration that grew more pronounced with each wheel revolution. He immediately began reducing speed, but the damage was already progressing. The left side connecting rod developed a stress fracture that propagated through the metal with terrifying speed. When the rod failed completely, it separated from the driving wheel with enough force to tear through the locomotive's running board. The broken metal whipped through space that seconds earlier had been occupied by the firemen checking coal levels. The rod struck the cab's rear wall, puncturing the steel plate and missing the crew by less than 3 feet. The locomotive's remaining connecting rods, suddenly bearing unbalanced loads, began their own destructive oscillations. Harrison executed an emergency stop that brought the wounded machine to rest after 3/4 of a mile of controlled deceleration that prevented complete mechanical disintegration. The connecting rod damage was catastrophic, but the crew survived uninjured. The inquiry that followed identified the fundamental problem that had defeated every previous attempt to achieve sustained high-speed operation with steam locomotives. At velocities above 100 miles per hour, the reciprocating motion of pistons and connecting rods created oscillating forces that overwhelmed the mechanical dampening built into conventional locomotive designs. British railway engineers calculated that reaching 120 miles per hour would require reducing these oscillating forces by at least 30%, while simultaneously increasing the power output needed to overcome aerodynamic drag that increased with the square of velocity. The mathematical requirements seemed impossible to satisfy within the constraints of steam locomotive technology. Sir Nigel Gresley studied the wreckage with methodical attention that his staff had learned to recognize as the prelude to revolutionary design changes. The conventional wisdom said steam locomotives had reached their maximum safe speed. Gresley would prove that conventional wisdom had missed possibilities hidden in aerodynamic principles that railway engineering had never properly applied. The design sketches that appeared on Gresley's drafting table in late 1934 provoked immediate controversy within the LNER engineering department. The proposed locomotive bore almost no resemblance to traditional British steam engines, its mechanical components hidden beneath streamlined casing that extended from smokebox to cab. Senior engineers argued that the streamlining was unnecessary weight that would reduce the locomotive's power-to-weight ratio without providing meaningful performance benefits. Wind resistance, they insisted, was a minor factor compared to the fundamental mechanical limitations that made high-speed operation dangerous. The proposed design seemed to prioritize aesthetics over engineering substance. Gresley's response filled 14 pages with aerodynamic calculations that demonstrated how wind resistance consumed increasingly large portions of available power as velocity increased. At 60 miles per hour, a conventional locomotive used approximately 15% of its power overcoming air resistance. At 100 miles per hour, that figure exceeded 40%. At 120 miles per hour, wind resistance would consume more than half the engine's output, unless the locomotive's shape was fundamentally redesigned. The streamlined casing wasn't decorative. It was essential to achieving speeds that conventional locomotives could never reach. But aerodynamic efficiency alone wouldn't solve the oscillation problems that destroyed connecting rods at high velocities. Gresley needed mechanical innovations that would reduce the violent reciprocating forces while maintaining the power output required for sustained high-speed operation. The solution emerged from studying the failure patterns of previous high-speed attempts. Conventional locomotives used 2 cylinders driving the wheels through connecting rods that operated 90 degrees out of phase. This arrangement created pulsating power delivery that became increasingly violent at high speeds, with each piston stroke generating forces that the locomotive's frame struggled to absorb. Gresley proposed using 3 cylinders instead of 2, with the middle cylinder driving the center axle and the outer cylinders driving the front axle. The 3-cylinder arrangement, with pistons spaced 120 degrees apart, would produce smoother power delivery that reduced peak forces on individual components. The mechanical violence that destroyed conventional locomotives at high speeds would be distributed more evenly across the entire machine. Critics pointed out that three-cylinder locomotives were heavier, more complex, and more expensive to maintain than conventional two-cylinder designs. The additional mechanical complexity seemed to contradict the reliability requirements that railway operation demanded. American engineers had experimented with three-cylinder designs and largely abandoned them due to maintenance difficulties that outweighed performance advantages. But Gresley had calculated that the three-cylinder arrangement, combined with careful component balancing and streamlined aerodynamics, could reduce the total mechanical stress at 120 miles per hour to levels lower than conventional locomotives experienced at 90 miles per hour. The mathematics was elegant, but translating theory into functioning hardware would require manufacturing precision that British railway workshops had never attempted. The final design element provoked the strongest opposition from traditional railway engineers. Gresley proposed installing a double-chimney exhaust system that would improve boiler efficiency by creating stronger draft through the firebox. The system had never been tested on high-speed locomotives, and critics warned that the additional complexity would create maintenance problems without delivering meaningful performance improvements. Gresley authorized construction of the first A4 class locomotive in December 1935, knowing that his reputation and possibly his career depended on the performance of engineering concepts that the railway establishment considered unnecessary complications to proven steam technology. September 27, 1935. The first A4 class locomotive, christened Silver Link, rolled out of Doncaster Works with streamlined casing that gleamed under autumn sunlight. The press photographs emphasized the machine's radical appearance, but railway engineers focused on the untested mechanical systems that would determine whether Gresley's theories translated into reliable performance. The inaugural high-speed run was scheduled for the following day, carrying a train of dignitaries and railway officials who would experience firsthand whether streamlined design justified its additional complexity and cost. Gresley positioned himself in the cab, determined to monitor every aspect of the locomotive's behavior during its first serious test. Silver Link accelerated smoothly through the first 50 miles per hour, its three-cylinder arrangement producing the steady power delivery that Gresley's calculations had predicted. The streamlined casing reduced wind resistance noticeably, allowing the locomotive to reach 70 miles per hour with less steam consumption than conventional engines required for the same velocity. At 90 miles per hour, the critical test began. This was the speed where conventional locomotives started experiencing the dangerous oscillations that led to mechanical failure. Gresley felt the familiar vibrations beginning, but they remained controlled, damped by the three-cylinder arrangement's smoother power pulses and the precise component balancing that had consumed weeks of workshop time. The locomotive passed 100 miles per hour with mechanical behavior that remained surprisingly stable. The oscillations were present but manageable, nothing like the violent shaking that had destroyed connecting rods on previous high-speed attempts. The streamlined casing proved its worth as wind noise decreased dramatically compared to conventional locomotives at similar speeds. At 112 miles per hour, Silver Link achieved the fastest speed ever recorded by a British steam locomotive. The mechanical systems continued functioning normally, the three-cylinder arrangement distributing forces evenly across components that showed no signs of the stress concentrations that plagued two-cylinder designs. The braking system brought the train to a controlled stop that demonstrated the locomotive's stability even during rapid deceleration. The success seemed to vindicate Gresley's unconventional approach, but the trial also revealed limitations that would prevent immediate attempts at higher speeds. The boiler, while adequate for sustained 100-mile-per-hour operation, struggled to maintain steam pressure during acceleration to 112 miles per hour. The fireman had to work continuously to keep the firebox supplied with coal, suggesting that reaching 120 miles per hour would require improved boiler efficiency. The double-chimney exhaust system Gresley had proposed for later A4 class locomotives became essential rather than optional. The increased draft would allow the boiler to generate steam more efficiently, providing the power needed for sustained high-speed operation without exhausting the crew or depleting coal supplies too rapidly. Railway officials who had been skeptical of streamlined design acknowledged that Silver Link had demonstrated capabilities conventional locomotives could never match. But they also understood that proving steam engines could safely exceed 100 miles per hour was different from achieving the 120-mile-per-hour speeds that would establish new world records. The Mallard, locomotive number 4468, would incorporate every lesson learned from Silver Link's trials. The double-chimney exhaust, refined component balancing, and improved boiler capacity that would finally break through the speed barrier that railway engineers had considered absolute. July 3, 1938 began with careful preparation that left nothing to chance. Driver Joe Duddington had been selected for his smooth handling and experience with A4 class locomotives. Fireman Tommy Bray understood that maintaining consistent steam pressure during high-speed operation would determine whether the attempt succeeded or failed. The test run would follow the East Coast Main Line south from Grantham, taking advantage of the gentle downgrade through Essendine that would allow maximum acceleration without excessive coal consumption. The train consisted of the Mallard and 6 coaches loaded with railway officials and dynamometer equipment to record precise speed measurements. Gresley rode in the coaches, unable to observe the locomotive's behavior directly, but trusting Duddington to execute the carefully planned acceleration profile that would bring the train to maximum velocity through the measured section. The attempt would either vindicate 3 years of A4 class development or demonstrate that steam locomotives had finally reached their absolute limits. The Mallard departed Grantham at 4:15 p.m., accelerating smoothly through the initial miles while Bray built steam pressure to the maximum the boiler could safely maintain. The double-chimney exhaust created a powerful draft through the firebox, allowing the boiler to generate steam at rates that single-chimney locomotives could never achieve. At Stoke Summit, 90 miles per hour indicated on the speedometer, Duddington allowed the locomotive to accelerate freely down the gradient toward Essendine. The streamlined casing reduced wind resistance exactly as Gresley had calculated, allowing the Mallard to reach 100 miles per hour without hampering speed. The speed continued building, 110 miles per hour through Little Bytham, 115 miles per hour approaching Essendine. The oscillations remained controlled, the 3-cylinder arrangement distributing forces evenly, while the precision-balanced components operated without the dangerous vibrations that destroyed conventional locomotives at these velocities. At milepost 90.25 south of Little Bytham, the dynamometer recorded 126 miles per hour. The Mallard had exceeded the world speed record for steam locomotives, achieving velocities that railway engineers had declared impossible just 3 years earlier. The mechanical systems continued functioning normally, demonstrating that the A4 class design had successfully solved problems that had defeated every previous high-speed attempt. Duddington maintained maximum speed for several seconds before beginning controlled deceleration. The braking system, designed specifically for high-speed operation, brought the train to a smooth stop that demonstrated the locomotive's stability even during rapid velocity changes. But the record came with a cost that became apparent during post-run inspection. The extended operation at maximum speed had overheated the middle big end bearing, causing damage that would require complete replacement. The Mallard had proven that 126 miles per hour was achievable, but sustaining such speeds would demand mechanical improvements beyond what the original design provided. Railway officials acknowledged that the record run had demonstrated steam technology's ultimate capabilities. The Mallard had reached speeds that diesel-electric locomotives of the era could not match, proving that steam power still possessed advantages that newer technologies had not yet overcome. But they also understood that the big end damage revealed the fundamental limitations that would eventually make steam locomotives obsolete despite their impressive speed capabilities. The weeks following the record run brought intense scrutiny from railway engineers worldwide, who sought to understand how the Mallard had achieved speeds that conventional wisdom declared impossible. Technical journals published detailed analyses of the A4 class design, identifying the specific innovations that had overcome limitations inherent in traditional steam locomotive construction. The streamlined casing reduced aerodynamic drag by approximately 35% compared to conventional locomotives of similar power. Wind tunnel testing confirmed that the carefully shaped nose and smooth body panels channeled airflow around the locomotive with minimal turbulence, reducing the power required to overcome air resistance at high speeds. The three-cylinder arrangement proved crucial to maintaining mechanical stability at velocities that destroyed two-cylinder locomotives. By spacing power strokes 120 degrees apart rather than 90 degrees, the design reduced peak forces on individual components while maintaining smoother overall power delivery. The reduction in mechanical violence allowed the Mallard to operate at 126 miles per hour, with stress levels comparable to conventional locomotives at 90 miles per hour. The double-chimney exhaust system increased boiler efficiency by creating stronger draft through the firebox, allowing steam generation rates that single-chimney designs could never achieve. The improved efficiency meant the locomotive could sustain high power output without exhausting coal supplies or overwhelming the fireman's ability to maintain consistent firing rates. Precision component balancing eliminated the vibration sources that caused catastrophic failures in earlier high-speed attempts. Every reciprocating part was weighed and machined to exact specifications, ensuring that forces generated during operation remained symmetrically distributed across the locomotive's frame. The careful balancing, combined with the three-cylinder arrangement, created mechanical harmony at speeds where conventional locomotives experienced destructive oscillations. German engineers acknowledged that the A4 class design represented genuine innovation in steam locomotive technology, achieving performance that their own high-speed locomotives could not match. American railway officials noted that the Mallard's record exceeded speeds their diesel-electric locomotives could sustain, though they remained committed to diesel technology for long-term operational economy. The big end bearing damage revealed during post-run inspection sparked debate about whether 126 miles per hour represented steam technology's absolute limit or merely the maximum achievable with existing materials and lubrication systems. Gressley proposed modifications that would allow sustained operation at record speeds, including improved bearing designs and enhanced lubrication systems. But railway economics were shifting away from speed records toward operational efficiency and maintenance costs. The outbreak of World War II in 1939 redirected resources toward freight and military transport, ending the era of high-speed passenger service that had motivated the A4 class development. The Mallard's record would stand not because later locomotives couldn't exceed it, but because the railway industry lost interest in pursuing higher speeds. The locomotive was withdrawn from service in 1963, having completed over 1 million miles of operation that demonstrated the A4 class design's reliability and durability. The big end bearing damage from the record run had been repaired within weeks, and the locomotive subsequently provided 2 to 5 years of dependable service that vindicated every aspect of Gressley's unconventional engineering approach. The Mallard speed record has endured for 86 years, outlasting the steam locomotives that followed it and surviving into an era when diesel-electric and electric traction have completely replaced steam on the world's railways. No steam locomotive has exceeded 126 miles per hour, despite technological advances that have transformed every other aspect of railway operation. Several factors explain the record's longevity, starting with the simple fact that steam locomotive development ended before engineers could apply modern materials and design techniques to high-speed operation. The diesel-electric locomotives that replaced steam offered operational economy and maintenance advantages that outweighed pure speed capability, shifting railway priorities away from record-breaking toward sustainable efficiency. Modern heritage railways operating preserved steam locomotives lack both the infrastructure and the insurance coverage necessary for high-speed record attempts. The risk of failure and the potential cost of accidents make record-breaking attempts economically unjustifiable, even though modern materials and computer-aided design could potentially produce steam locomotives capable of exceeding the Mallard's achievement. The record's preservation reflects changing values in railway engineering, where 1930s railway companies competed aggressively for speed records and public attention. Modern operators prioritize safety, reliability, and environmental sustainability. Breaking the Mallard's record would demonstrate technical capability, but provide no practical benefit to contemporary railway operation. The locomotive itself survives as a museum exhibit at the National Railway Museum in York, its streamlined casing still gleaming despite decades of retirement. Visitors can examine the engineering details that made 126 miles per hour possible. The three-cylinder arrangement, the double-chimney exhaust, the precision-balanced components that distributed forces evenly at unprecedented speeds. Engineering students study the A4 class design as an example of how systematic analysis and careful innovation can overcome limitations that conventional wisdom considers absolute. Mallard proved that steam technology possessed capabilities that even experienced railway engineers had failed to recognize, demonstrating that mature technologies can still yield revolutionary advances when approached with fresh thinking. The record run represented steam locomotive engineering's final triumph, achieved just before diesel-electric traction rendered steam obsolete for commercial railway operation. Had the record attempt come 5 years later, wartime restrictions would have prevented it. 10 years later, railway companies were already replacing steam with diesel, eliminating the incentive for high-speed development. The timing was perfect, capturing steam technology at its absolute peak before economic and technological forces shifted the railway industry toward different priorities. The Mallard demonstrated what steam locomotives could achieve when engineering excellence was applied without compromise to mechanical design, aerodynamic efficiency, and operational planning. 86 years after the record run, the fundamental question remains whether any steam locomotive will ever exceed 126 miles per hour. Modern technology could certainly produce a machine capable of higher speeds, but the economic justification and operational necessity have disappeared. The Mallard's record endures not because it represents steam technology's absolute limits, but because railway engineering has moved beyond the era when speed records mattered. The locomotive that experts said could never safely exceed 120 miles per hour achieved 126 miles per hour through systematic engineering that refused to accept conventional limitations. That achievement remains unmatched, a permanent reminder that declared impossibilities sometimes yield to careful analysis and determined innovation.